Okay, Art22, here we are again. Now today we have a shorter sketch to work on in terms of lines of code. But I will warn you, the concept behind it takes a moment to get your brain around. It's a little bit more complicated than some of the other movements that we've seen in the past 3 lectures. We're going to be dealing with something called noise. Now, noise is a lot like random, but there's some differences. And so the result of what we're going to have today is another sketch where a point is moving around on our screen, but instead of using the random function to give it this kind of complex, unpredictable behavior, we're going to be using a different function called noise that has its own sort of characteristics. And we're going to see that it has a bit more of an organic feel to it. It's less random. It's a randomness that's less random. We'll see what that means in a little bit. But first of all, let's just talk a minute about the differences between random and then what we're going to use today, which is noise. They're both functions that are built into processing. But let's take a look. Let's plot out like we would a graph in math or physics class or something like that. So let's say that I have a graph here where we have time on this axis here. I'm sorry if this is giving you nightmare flashbacks to math classes of old. But so we have time going left to right, and we have value, so a number on the y-axis. Okay. Now, let's say that every time that I say now, I'm going to use the random function, which we've seen before, to get a random number between, let's say between 0 and 1. We'll make it really easy for ourselves. So we know that random gives us floating numbers, so we could have anything from like 0.1 or 0.1112 all the way up to 0.998, something like that. So random is going to give us random numbers between 0 and 1, but it's going to be very random in the sense that it could be anywhere in between them. So maybe it would look like this. So the first time I say, give me a random number, maybe it gives us maybe that's like 0.5 or something like that. Now the next time I say give me a random number, maybe it gives me all the way up here at like 0.8 or something like that. So this is 1, and this is 0. Maybe the next time I ask for a random number, it's going to give me, who knows, maybe it gives me almost 0.8 again. Next time, maybe it's way down here at like 0.01 or something, and so on. So we can see that random is like really all over the place. Every time, at every point in time that I ask for a random number, I could have anything between 0 and 1. And we saw that a little bit with our random walk, that it was really jittery, right? Because it's jumping around all over the place. Sometimes I like to think about it as like as a person that could like teleport or apparate, if you are a Harry Potter fan. And so they can move at any given point to anywhere around here. Like it could be, 2 blocks that way, then 4 blocks that way, then right here on this table. They could be doing, they could be anywhere. So that's kind of like the random function. It could be any possible number within that span. Now here's the big difference when we go to noise. The way that the noise function works is it's going to have our values that we get, our random values, they're going to have a closer relationship to each other based on time. So that's kind of a weird thing to think about. It's easier to see it when it's drawn out. So here's that was our random. Okay, now let's look at noise. Oops, that's not how you spell noise. Nosy. Noise. Okay. So let's do the same thing. We're going to say time. We're going to ask for a bunch of noise values that will still be between 0 and 1. Okay. So let's say the first value I asked for, give me a noise value here at this time. Maybe I'll get something like that, 0.5 or something. All right, at the next point in time, I want another noise value. It's going to give me something like this. Another noise value, maybe something like that. Maybe something like that. So, I mean, I'm making these up just because I know how the noise function works. But what you're going to see with noise is that there's a stronger relationship between the values that came before it and the ones that will come next than there is with the random function. Random could be anything within a range of 0 to 1. Noise is going to have, between the previous one and the next one, it's going to be closer than it was with random. So that's why you see on this graph of noise, it's kind of this smoother shape because of the values that you're getting are closer to its neighbors. So if we think about our person that's teleporting all over the place, every step of time, they could be 4 blocks that way, 2 blocks that way, 1 block that way. With noise, imagine it as it's not that they can't teleport now, it's now that they can only run, right? So if I'm giving, okay, now where are you? Now where are you? Now where are you? If you could teleport, you could be anywhere. If you can only run, you can only be a certain distance away from where you were previously or where you will be next. So if I'm the person now that's our noise function, I mean, you could say now, and however long, I could run from this room to that room maybe, but I can't go much further than that. So that's the way I like to think about it, is noise is going to give you values that are closer together, are kind of grouped closer together, so you get a much smoother range of numbers than random, which is going to give you all over the place. And so why are we doing this? We're doing this because of this additional attribute of noise where things are a bit more similar, these values over time. We get a very organic, kind of smooth nature to the results when we use noise instead of random. Random, we get all over the place craziness. Noise, we get a smoother, it's still unpredictable, it's still complex, but it's kind of a smoother type of randomness. We're not going crazy, we're kind of gently going through different random numbers. So that's the way I like to think about it. So what we're going to do today is just basically do the bare minimum way to implement noise into drawing a point. And it's going to cover a couple new things that we haven't seen before. But again, this is one of the more complicated topics that we're going to kind of be implementing. So get plenty of practice on it, ask questions, but let's go ahead and try it out and see if we can get noise to be controlling the position of our point, just like we did in the previous lecture. All right, so let's jump into it and see what we get. Okay, here we are. Now let's do all the normal things, right? We're going to do our setup, our draw, let's do a size, okay. Alrighty, so we know that we're going to be drawing, let's do a point again. Let's keep it very similar to the previous random walk lecture. So I'm going to do a background of 193, 98, 108. So have the same background as before. Now we're going to have a stroke weight again because we're going to be drawing a point. So stroke weight of 4. Actually, I think we used 10 last time. Let's stick with that. And stroke, why don't we just use white for now? And then we finally draw a point. Okay, so we need our variables like we saw in the last lecture. So I'm going to say, we're just going to draw one point today, so we're just going to use x and y. So I'm going to say float x and y position. And let's get a initial condition, and let's do what we always do, which is x is going to be in the middle, and y will be in the middle. Okay, great. So let's confirm things are running. Good, okay, there's our point. Okay, so what we need to do is see what happens when we actually run this noise function. So, you know, let's just see what we get when we actually print out a result from the noise function. So I'm going to make a variable called, how about float? Could be really anything. So a lot of times you'll find this convention that people will use, because we're going to have two of these. We're going to have a noise value for x and a noise value for y, just like we had a random for x and a random for y in the last lecture. People tend to use letters that are next to each other in the alphabet when they're related. So like I and J, or N and M, things like that. So maybe for now I'll do M, just kind of randomly. And that's going to equal noise. Okay, and let's say, I'm going to put in a 0 here, and we're going to dissect this in a second. Okay. So why don't we do this? I'm going to print out what that gave us. So print line M. Okay. All right, so we got this number, 0.363989923, over and over and over and over and over again. Okay, so that's kind of strange, right? Because when we had our random function, we would get all sorts of numbers all over the place. Just to prove that point, I'm going to slow down my frame rate for a second just so we can see things very slowly. So I'm going to say frame rate is 2 frames per second. There we go. So now you see that we have a new random number, but it's the same. This 0.314057537. Let's look at what would happen if we printed a random. So we're going to say, how about instead of float m equaling noise, we're going to say float m equals random between 0 and 1. Now we'll print m. Let's see what we get. All right, so now we're seeing different numbers. Interesting. So let's switch back over to the other screen here. So this helps to illustrate the big difference in terms of how we use noise and random. Random, remember inside the parentheses, we just need to tell it the range. So random between 0 and 1. And so every time that function runs, it's going to give us a new random number. The big difference with noise is noise, it's almost like the noise values are already determined. We need to just tell it what point in time we want a noise value. That sounds pretty crazy, right? But let's look at it again. I think it makes more sense visually. So here we have noise. And so we said in this example 0. That's what we wrote in our code before. So what is 0? 0 is not the range anymore because noise, if we looked at the reference, we'd see this. Noise is always going to give us a value between 0 and 1. That's already by default. That's just like how it is. So what are we actually then giving it when we pass this argument, when we put in that 0 in between the parentheses? What that's saying, weirdly enough, is that's the point in time that we want a noise value. So again, let's look at this visually. All right, so remember that we said in our little graph here that was time going to the right. So what we said was give us the value at 0. Give us the noise value at 0. That happened to be, let's say it was there, maybe that was point, I don't know, 5 or something like that, 0.56. Okay. Now, what if I said, give us noise 1? Well, so that was 0. Now we want the one that's at 1. So now the noise value at 1 is there. Looks like a little bit bigger. So maybe that was 0.58. Now, noise 2. So our noise value at 2 is that. Looks a little bit bigger yet, so that's maybe like 0.59, let's say. So that's what we're saying when we say noise and then we give it a value. It's what point in time, so where are we along this line of values for noise? You know, 0's over here, give us that value. The noise line is going like this. Maybe we're at noise 10, what's that value? So that's how we're going to be getting values from noise. We have to think about it in terms of where along this kind of infinite line of values are we going to be asking for a value. I know that's a little bit of a complicated idea. We can talk about that further, but know that that's what we're passing to noise. We're passing the location along that line of what value we should be getting. So let's put this into code and see how that works. Okay, so we don't want random right now. We'll get rid of that. Let's go back to our noise. So we found out that if this value doesn't change, we're just going to keep getting that same noise value at location 0 over and over and over again. So what we would want to do if we wanted to get new numbers, we would need to start changing this value inside of there. So why don't we make this a variable instead of just a number? And let's call this float noise position, noise pos. So we'll say position of noise value. Okay, so I'm going to take this variable, noise pos, and put it into here. Okay, and let's set that variable to be 0 at first. All right, so we're starting at like the beginning of our noise line, but now we want to increase so that we're getting new noise values. And so how can we do that? Well, we can just increase this variable. So we can say noise equals noise pos plus some amount. So it's going to get a little bit bigger each time. And so the question is then, like, how much do we want to increase it? Do we want to increase it by 1? Do we want to increase it by 20? Do we want to increase it by 0.0001? The answer to that is kind of up to you depending on what kind of behavior you want. The larger we increase noise by, that means the further along the line that we have traveled. Let's take a look at this again. So the bigger we increase noise by each time, the further along that line we'll have gotten. So in this case, we saw that we increased noise by 1 each time, at least in this situation. And so we were getting numbers that were pretty close to each other. You can imagine, what if we increased noise by 10? So if we went from 0 to 10, to 20. In that case, we would have started here at, like whatever, 0.566. Maybe 10 for there is like that one, which is maybe 0.3 something, maybe 0.32, let's say. So there's a bigger difference between those numbers because we've traveled further along that noise line. So the smaller your increase in your noise position, the closer together those numbers will be, and thus the smoother your randomness will be. The larger you increase your noise position, that means the further apart those values are likely to be, which means that your randomness is going to be choppier and a bit more chaotic. So given that, let's go back to our code. Given that, let's increase our noise by a very small number. How about 0.001, something really tiny. And then I'm going to put this at 1 frame per second. And then let's print out this noise value that's getting bigger by 0.001. Okay, so 0.56. Okay, let's stop it there. So we can see that the first, 7 or so values we got were very close together. 0.619, 02, 9048, 919, so very, very close together. Let's go ahead and make this bigger, so 1. Aha, okay. So now each value we get, it's still a lot close, like much closer together than our random function, but we are getting a bigger variety here. We're going from 0.44, 0.48 or 9, 0.6, 0.3. So now we're actually getting much more randomness and less smoothness in our results. So the whole point of using noise, at least in this context, was to have a more smooth version of noise. So let's keep it back to 0.001. Okay. All right. So that's kind of the hard part of today. Getting the conceptual idea of the fact that we're getting a value from a noise function that's based on, it's kind of like the way we've been thinking about it, this location along a line, okay? So let's actually put this to some use. So why don't we say that we're gonna have, because we wanna work with both X and Y, we're gonna have a noise pause X and a noise pause Y. Okay. And let's go ahead and I'm gonna do this. We did float M was for, let's say, our noise pause X. Now we need to do the same thing for Y. Oops. So why don't we call it N? And we'll call this Y. So what is this doing? This is get a noise value for X position. And this will be get noise value for Y. Okay. Now we need to increase both of these, noise pause X, noise pause Y. Do the same thing for, oops, keep doing that. Do the same thing for the Y version. Don't need to print anything right now, so let's get rid of that. Okay. So here we are. We use noise to get random numbers that are smoothed out. And they're smooth because we're increasing our noise position by a very tiny amount each frame. Great. Okay. We need to adjust this. So our noise pause X initial location would be 0. If we did the same thing for noise pause Y, we'd end up getting the same thing because they're starting at the same point and then they're increasing by the same amount. So we're going to make the initial value of noise pause y something different. It could be anything, but I'm just going to say 100. How about? So you can think about it as like this noise position is starting at the beginning of our line, our noise line, whereas this is starting way over at 100 and getting bigger. So that now these will be different values. Okay, great. Now there's one last step we need to do to actually use this. So as you can see from the results we've gotten down here in the console, noise, and I mentioned this before, but noise gives us a value between 0 and 1. Now we want to be using this for to change the position of our point on the screen. So having 0 to 1 is not a really good range of possible positions. We want something like from 0 to width and from 0 to height, not from 0 to 1. If we were to run this, our particle, our dot, our point, would be stuck between 0 and 1 in the x direction and 0 and 1 in the y direction. So it basically looked like it was just up in the corner or not doing anything. So what we need to do is map the range of 0 to 1 to the full width of our screen. So let's take a look at how the map function works in processing, because they have it built in for us, which is great. Okay, so processing has a function called map. And what that does is it says, okay, so we have this value that exists currently in a range from, let's say, 0 to 1, like our noise value. So we get this noise value, it's between 0 and 1, but we want that to actually be between 0 and width for our full screen. So thankfully, processing has something called the map function that will do this for us. So here's how it works. So we have, let's say we have x is what we want. So we're going to say map. Now map takes 5 things. The first thing it takes is the actual value that we want to be mapping. So in this case, we want to map our noise value. So remember we called those m and n. So we're going to say, let's take m, which is the value we got from noise, which is between 0 and 1. So that's the first thing, is what value to map. And map, think of it like, what value do we want to convert? We can want to convert it from between 0 and 1 to being between 0 to width. So the next two things it wants is it wants the range of that value currently. So we know for the moment that the value that the variable m exists between 0 and 1 because noise function gives us values between 0 and 1. So it's like old range. The new range that we want it to be between is 0 to width. So the new range, 0 to width. And that's it. So these two are the old range, and these two are the new range. So think of it almost like processing, like stretching it out. So the value before was between 0 and 1, so anywhere between here and here. But now we want it to be between 0 and width, so it can be anywhere between these. So this is like a magic transformation function that's going to stretch that out for us. And so we would do the same thing for y, but just between 0 and height. So let's go ahead and put that in. Okay, so we said that we want to map these values. We want m to not be between 0 and 1, but between 0 and width. So we're going to say x, because that's our position variable, is going to be a mapped version. The value we want to map is m, that one is there. The old range, it used to be between 0 and 1, but we want it to be between 0 and width. So we're going to stretch that range to be the full screen. Now we just do the same thing for y. Y equals map, this time the n value between 0 and 1, it's old range. And the new range we want is height, because we want this to fill our entire screen, not just between 0 and 1. And then we use it, and we increase our noise position, and let's just see what we got here. Oh, I was like, why isn't that working? It's because our frame rate is still at 1. Okay, so let's get rid of that. Or actually, I'll leave that in there, but just comment it out in case you need to slow down your screen or your animation. Okay, I was like, why won't this work? So let's run this again. All right, and now we see that this little dot is moving around randomly, but in a much smoother way than it was with our random function. It almost, and like I mentioned at the beginning of the lecture, like how this is going to have a bit of a organic feel. To me, this has a more like, it looks like a little organism, right? Like it has like, it almost has like a little bit of logic to like why it's moving in these different directions. Now, what I think is very cool is when we actually show all the, like we did with the random walk, we show the previous locations. So I'm going to comment this out, and we're just going to draw our background here. Now let's take a look at what we have. There we go. So now we can see that we are getting random movement, but in a way that has a bit of more order to it. It's smoother. It's not so frenetic and chaotic. And so you could imagine changing the smoothness based off of how much we're increasing the noise position. But again, you can imagine, and we'll do this in future lectures, what would happen if we had, you know, a couple hundred of these points all moving with different colors and things. We get this really rich texture. Okay, so let's switch back over. Actually, we'll leave it up because it's kind of cool to watch. All right, so that was a much more technical topic than we'd seen in some of the previous lectures. It's just a way to show another possibility. I would say explore it, take this code and make tweaks to help yourself understand what's actually happening. But just know that it's just one method of many to get generative kind of movement from something that's built into processing, in this case, the noise function. Okay, so that is all for our movement week. We'll continue to add more things to this in future weeks, but now we have ways to move things on the screen that are based on straight lines. We have versions with like gravity or acceleration where they're parabolic motion. We have random walk, and now we have this noise method to give us this kind of lifelike sort of motion. All right, folks, that is all for today, and we will catch you next time.